Okay, greetings. Right, today what we are going to look at is the subject of snubbers. Now, mind you, when it comes to snubbers, there's two types of snubbers. There's what we call a turn off snubber as well as a turn on snubber. Now, to keep your transients within the safe limits of a device, snubbers delay the rate of rise of either voltage or current in a device. Okay, and they are fundamentally speaking used to minimize the power dissipated during switching times by means of wave shaping. Okay, right. So in this instance, we are going to start with what is called a turn on snubber. Okay, on the left, you will notice here is the circuit of a turn on snubber. Okay, you will also notice on the right hand side of the page we have the corresponding graph of the circuit. Okay, now on the graph you will notice, right, that over here there is what we call IT. This is the curve for IT, or it's a function that is describing IT. Okay, and then at that point we have another curve or another function, okay, that is describing I. When we talk about I, what exactly are we referring to? We are referring to the load current, as you'll notice here on the circuit. Okay, what is IT? IT, it's basically the current that is flowing via or through the transistor. Okay, right. Then you'll notice we also have VT over here. Okay, VT essentially speaks of a linear fall in voltage or a linear drop in voltage. Yeah, linear drop, not linear fall, but anyways, yeah, in voltage. Okay, then we will notice that we also have T1, we also have T2. Now, what is T2? T2, it's the time it takes for V to drop from supply level up until 0. Okay, what is T1? T1 it describes the time it takes for IT to equate into I supply. So simply meaning whenever the time it is taking for IT to be equal to I supply, that time we reference that as T1. Okay, now why is this important? This is important because the flyout diode will switch off when the current through it has reached or has been reduced to 0. I repeat, the flywheel diode, it will switch off, okay, meaning it's on. So it will switch off. When will it switch off? When the current through it has been reduced to 0. Now, in what instance will this case be true? It will be true when IT is equal to I supply. Simply meaning when IT, the current flowing here, is equal to I supply. Simply meaning I supply. There's no current going through or via the diode. Okay, alright. So this will happen when the transistor current equals the load current. And then all of this happens at point A, as I've depicted here on the graph. Okay, so for now, we've discussed snubbers, pointing out that there are two different types of snubbers. And then what we've shed light on is the fact that this circuit diagram, it's the circuit diagram of what is known as a turn-on snubber. Okay, we also pointed out to the fact that snubbers are essentially used to keep transients within the safe limits of a device. Snubbers delay the rate of rise of either voltage or current in a device, and this is fundamentally used to minimize the power dissipated during switching times by means of wave shaping. Now in the next video, what we are going to do is we are going to derive an expression for the inductance. When we say inductance, we are referring to that inductor over there. Okay, let me just put a L there. All right, we will derive an expression for the inductance L that will delay the rise of current to its on state value. Okay, yeah, so that is what we will do. We will basically derive an expression for the inductance. Why the inductance? The inductance because it is fundamentally used for the delay of the rise in current. Simply meaning current in a circuit will rise or voltage in a circuit will rise, and we are trying to delay the rate at which that increase or that rise is happening. And in this case, we will derive the formula for the inductance in order for that to be the case.